Dark matter plays a fundamental role in the formation, evolution, and structure of galaxies throughout the cosmos. Making up approximately 85% of the matter in the universe, this enigmatic substance shapes the cosmic landscape, despite being invisible and only detectable through its gravitational effects. Dark matter serves as the scaffolding upon which galaxies are built, providing the gravitational wells that capture normal matter and allow the first stars and galaxies to form. The theory of dark matter has become central to our understanding of how the universe evolved from the nearly uniform state after the Big Bang to the rich tapestry of cosmic structures we observe today. The following exploration details the critical importance of dark matter in orchestrating the birth and development of galaxies across cosmic time. At the heart of galaxy formation lies the concept of dark matter halos, hypothetical regions that have decoupled from cosmic expansion and contain gravitationally bound matter. These halos form the basic units of cosmological structure and establish the gravitational foundation that enables galaxy formation. A dark matter halo envelops the visible portions of a galaxy and extends far beyond the edge of its luminous boundary, creating an extensive gravitational field that influences both the galaxy's formation and its ongoing evolution. The presence of these halos is inferred primarily through observations of galactic rotation curves, which reveal that stars and gas at the outskirts of spiral galaxies move much faster than would be expected based solely on the gravitational pull of visible matter. Without large amounts of dark matter distributed throughout a roughly spherical halo, rotational velocities would decrease at large distances from galactic centers, similar to how planetary orbital speeds decrease with distance from the Sun in our solar system. However, astronomical observations consistently show that rotation curves of most spiral galaxies flatten out rather than decline, providing compelling evidence for the existence of massive dark matter halos. Under the widely accepted cold dark matter (CDM) cosmological model, galaxy formation follows a hierarchical bottom-up pattern rather than a top-down monolithic collapse. In this framework, small overdensities in the primordial universe were the first to overcome cosmic expansion and collapse, forming the initial dark matter halos. These early halos then merged together to create progressively larger structures, establishing sites where galaxies could eventually form. This process has continued throughout cosmic history and persists to the present day, making galaxy formation an ongoing phenomenon rather than an event confined to the early universe. The nonlinear collapse of dark matter over densities proceeds on increasingly larger scales as cosmic time advances, causing typical collapsed halo masses to grow over time. This hierarchical merging process fundamentally drives galaxy evolution, as dark matter halos accumulate mass through mergers and accretion, subsequently influencing star formation rates, gas distribution, and the overall dynamical states within galaxies. In the early universe, dark matter initially coalesced into an extensive web-like network of thread-like filaments spanning millions of light years. The exact behavior of these filaments varied according to the specific properties of dark matter particles. Under the cold dark matter model, these filaments quickly fragmented into clumps, causing protogalaxies to emerge as separated clusters of stars. The formation pathway from dark matter structures to luminous galaxies follows a complex sequence. Initially, dark matter and normal baryonic matter, gas, were well mixed in the early universe. As gravitational fluctuations intensified, this mixture began to separate, with gas gradually descending toward the centers of forming dark matter halos due to its ability to dissipate energy through radiation, something dark matter cannot do. In particularly massive dark matter halos, the concentrated gas at the core could cool significantly through various emission processes, allowing it to contract further and eventually reach densities suitable for star formation, giving birth to protogalaxies. The characteristics of dark matter halos profoundly shape the properties of the galaxies they host. The mass distribution and abundance of these halos directly determine both the rate and quantity of galaxy formation throughout cosmic history. High-mass halos typically retain more gas available for star formation, while low-mass halos may lose substantial portions of their gas due to feedback processes from stars and supernovae, leading to decreased star formation efficiency. Dark matter stabilizes galaxies by providing the gravitational force necessary to maintain the orbital motion of stars and gas. A higher proportion of dark matter results in increased galactic rotation speeds, further enhancing stability and preventing the disintegration that would occur if galaxies contained only visible matter. Additionally, the distribution pattern of dark matter ensures that galaxies experience consistent gravitational forces during their formation, contributing to the development of relatively regular and symmetrical structures. Beyond individual galaxies, dark matter orchestrates the formation and evolution of large-scale cosmic structures. The hierarchical merging of dark matter halos facilitates the creation of galaxy clusters containing hundreds or thousands of galaxies bound together by gravity. Within these enormous structures, galaxies gravitationally interact and sometimes merge, further enhancing galaxy formation and evolution processes. Dark matter's gravitational effects can also bend space, creating observable gravitational lensing phenomena that provide additional evidence for its existence and distribution. Modern cosmological simulations, such as Illustris and Illustris TNG, demonstrate dark matter's crucial role as the backbone of galaxy formation, with cold, dark matter models successfully reproducing many observed properties of the galaxy population. An intriguing aspect of dark matter's role in galaxy formation is that despite the lack of preferred scales in the distribution of dark matter halos, galaxies exhibit distinct minimum and maximum masses. This characteristic arises from the interplay between dark matter and baryonic physics. While dark matter provides the gravitational framework, processes involving normal matter, such as gas cooling, star formation, and various feedback mechanisms, introduce physical scales that constrain galaxy sizes and masses. This balance between dark matter's structuring influence and baryonic physics' regulatory effects produces the diverse yet patterned galaxy population observed in our universe, from dwarf galaxies to giant ellipticals. In conclusion, dark matter serves as the cosmic architect that enables and shapes galaxy formation through its gravitational influence. From providing the initial density perturbations that seed structure formation, to establishing the hierarchical assembly pattern of galaxies and organizing them into clusters, dark matter's invisible hand guides the visible universe's evolution and structure. Understanding the precise nature of dark matter remains one of modern astrophysics' greatest challenges, yet its fundamental role in galaxy formation stands as one of cosmology's most significant insights.